Let me describe the question. We are given this function y is equal to square root of 2 times inverse tangent x times root 2 over x plus 2. So we're given this equation for y. Okay, we need to do a few things. First, we need to show that this equation is true, that x bracket x squared plus 2x plus 3 close bracket and then dy dx is equal to 2. We need to show this. Next part, we need to find the by differentiating this, we need to find the Maclaurin series. We need to find this series to x up to x cubed. And then for this expression, 1 over x squared plus 2x plus 3, this expression, we have to find the first 3 non-zero terms. So these are the 3 things that we have to do. Let me start with the first. Now for the first thing, we have to we would most likely have to find the dy to differentiate this to get the dy dx and then show that this is true. Let me start with that. So to differentiate inverse tangent of x, let's recall the formula for inverse tangent of x. Now if you have memorized it, that's fine, just use it, but I normally try to I normally have to work it out in case I forget. So let me just quickly write this out. If y is inverse tangent of x, so this y is not the same as that y, this is a separate working, then tangent y is equal to x, then we get if I differentiate this dx dy, I get second squared y. Okay, so dx dy, so second squared y is actually 1 plus tangent squared y. Okay, which tangent y is just x, so this is 1 plus x squared. So then inverting that gives dy dx, which is 1 over 1 plus x squared. So this is the formula for the dy dx, and y is inverse tangent of x. So let's just remember this is 1 over x squared. Okay, clear that? So that means that if this is just x, then it will be 1 over x squared times the root 2. But it's not just x. It's not just x. So this is actually, the argument is actually a function of x. So that means we must use the chain rule to differentiate this the arguments after we have differentiated with respect to the whole thing. So let me write this out. So dy dx, we have the root 2 factor here. It'll be 1, I'll start with 1 over 1 plus the argument squared, which was the formula I got just now. 1 over 1 plus this thing squared. So x root 2 x plus 2 squared. And then times the derivative of this. Okay. So let's see. So I can do that by multiplying, by differentiating this. So let me work through this quickly. So this would be using, say, the quotient rule. I'll get x plus 2 squared at the bottom, and then x plus 2 here times differentiate that, minus, and then that times differentiate this. So x root 2, differentiate that is just 1. So this is what we'll get. Okay. And I have x root 2 here and I have an x root 2 here, so they cancel. And then the root 2 there. Times 2. I missed out something. That should actually be a 3. Yes, that should be a 3. So 3 here, 3 here, and that should be a 3 there. Okay, so the x times root 2 and x times root 2 here cancel. I still have a root 2 there, and what remains here is a 3 root 2, and this multiply into here gives x plus 3 squared. This and this cancel to give x squared times 2. Okay, so that's what we have. And yeah, fine. So if I expand this, I'll get root 2 is 2 times 3, 6, divided by, expand this, I get x squared plus 2x squared, that's a 3x squared, and then x times 3 times 2 is plus 6x, and 3 squared is a 9. So if I then divide the top and bottom by 3, I get 2 over x squared plus 3x plus 3. Okay. And so now I have dy dx is equal to this. And if I rearrange this, I would get the first answer to the first part of the question just now. So let me say that, okay, so this is equal to this, right? So if I bring the denominator over to the other side, or just multiply both sides by the denominator, I'll just put equal to dy dx here as well. So move this over to the other side. I get 2 is equal to move this over to the other side. Okay, I get x squared plus 3x plus 3. Oh no, wait. So that's I have to divide that by 3 and each of these by 3. So wait, that should be a 2 there. That should be 2 there, and 2x plus 3 here, and that's dy dx. So that's the first answer to the first part of the question. Okay, and let's move on to the next part. The next part, we need to find the Maclaurin series for y. So the way to do that is to make use of this. We have already differentiated with respect to we have already differentiated y by x once to get this. So to find the Maclaurin series, we have to differentiate again, maybe a few times. And we need to do it up to x cubed, so we have to differentiate 3 times to get the third derivative. Now, in principle, we can just keep differentiating this again and then again. But it's actually easier to differentiate this, because this one involves a fraction, and it's always more complicated to differentiate fractions, as you have seen. We need to use the quotient rule, which is a bit messy. Okay. So let's do it by differentiating this implicitly. Okay, let's see how to do that. Let me just clear this. There's a 3 there, actually. So let me start by writing out that expression again. We got x squared plus 2x plus 3 dy dx plus 2. So that's what we got for the first part of the question. Now we want to find the Maclaurin series, and we need to differentiate this again. We need to differentiate y up to 3 times. So I'll do it by differentiating this whole equation. So let's see how it works. If I differentiate, say, the left hand side, using the product rule. So I start by saying, let's recall the product rule. Let's see, d by dx of uv is equal to u dv over dx plus v du over dx. Okay, so u and v would be like this and this. So this would be like the u, and that would be like the v. So I would keep this one unchanged for a start and differentiate that. So I get d2y over dx squared. And then I would keep that unchanged and differentiate this. This gives me 2x plus 2. Okay, and then dy dx is not changed term. On the right side, when I differentiate this, I'll get 0. So in this way, I've got an equation that contains the second derivative. Now I don't actually have a direct formula for it, but if I can find dy dx first from there, then I can use the answer from there in here and calculate, and still be able to calculate d2y dx squared. Okay, and I need d3y dx cubed, because I need this up to x. I need to expand this series up to x cubed. So I need to differentiate this again. Okay, let's carry on. Once again, applying the product rule to this, I have a product of this factor and this factor. So I start by keeping that unchanged, x squared plus 2x plus 3, and differentiating this. d3y over dx cubed plus, and then keep that fixed and differentiate this. So that gives x, I'll differentiate this, that gives 2x plus 2. That differentiates the 0, and that's unchanged. d2y dx squared. The next thing is to differentiate this. Again, using the product rule. So the two factors would be this one and this one. Now if I keep this unchanged and differentiate this, notice that I get exactly this, right? This unchanged and differentiate this. Okay, so this means that I would add a term that looks exactly the same as this. So I might as well just put a 2 there. Plus, and then I differentiate this factor, keeping dy dx unchanged. Differentiating this, just give 2 dy dx. So now I have an equation that contains the third derivative. That's all I need. So once we got this, let's start calculating the values of all the derivatives when x is 0. Okay, so when x is 0, let's see what happens. Clear this out. Okay, when x is 0, y would be y from here would be 0, because inverse tangent of 0 is 0. Okay, then the next term, the next derivative, first derivative, dy dx. When x is 0, let's put in the 0 there and there. Okay, then we'll be left with 3 in this bracket. And if I bring the 3 over, I get 2 over 3. So dy dx is 2 over 3. Okay, so I have dy dx now, and I can substitute it into here. Okay, so when x is 0, that will be 0, and then I have a 2 there, and I have a 2 over 3 here, and x is 0, I have a 3 there. Okay, so those two terms will go to 0 and just have the 3. That goes to 0, just have 2. 2/3 goes into here. So this gives 3 d2y over dx squared plus 2 times 2/3, which goes into here. Okay, so then we can solve for d2y dx squared. That's 4/3. Bring that over, and then bring the 3 over as well. I get minus 4 over 9. So I have this as I have the second derivative now. And finally, we can use this last equation to find the third derivative. Okay, when x is 0, that's 0, that's 0, that's a 3. x0, that's 0. So 2 here times 2 is 4. And d2y, dx squared is minus 49. Okay, and dy dx is 2/3. So then we can solve for d3y dx cubed. Okay, that would give 4/27. So now that we have these three derivatives, we are ready to write down the Maclaurin series for y. Okay, clear this. Maclaurin series y is equal to, so the first term, right, just to make things easier, let me quickly write down the formula for Maclaurin series. Fx is equal to f0 plus f first derivative f prime x plus 1/2 factorial f second derivative 0 x squared. We need to go up to x cubed. 1/3 factorial f third derivative 0 x cubed plus dot dot dot. Okay, so that is why f0 is that one. 0 f primed 0 first derivative is 2/3. This f double prime would be the second derivative, which is minus 49 plus 1/2 minus 49 plus that's 1/6 f third derivative, that would be this 4/27 x cubed plus dot dot dot. And that's it really. It's just a matter of simplifying the series. That gives y equals to 2/3 x minus 2/9 x squared plus, okay, let's divide, cancel these two, 2, 3. So divide that and that by 2. And 3 times 27 is 81. So that gives 1/81 x cubed plus dot dot dot. It's 2 there. Okay, so we have done the second part now. We have gotten the Maclaurin series. And finally, the last part. Okay. Let me clear this up. Now I would need to keep a few things. I'm just going to clear this. And clear that. Okay. So the last part, I need to expand this expression. One over x squared plus 2x plus 3. We need to expand this and find the first 3 non-zero terms. So plus 1 term, 2 terms, 3 terms. That's what we need to do. Okay, we can just do it directly using the Maclaurin series formula. But there would be a simpler way using by making use of this. If you notice that this denominator here is exactly the same as this bracket. Okay, so if you notice this, then you will realize that this is actually, if I move this over to the other side and move the 2 over there, if I cross multiply, so the 2 comes here and this one comes there, I'll get 1 over this on the right hand side, and on the other side I'll get half of dy dx. So this is actually equal to half of dy dx. How does that help? Okay, it helps because we already have the series for y. So we can actually find the series for dy dx just by differentiating the series for y directly, term by term. So let's do that. So this is equal to half, dy dx. So I would differentiate this. That gives 2/3. Differentiate that. So x squared gives 2x. 2 times 2 is 4, minus 4 over 9x. Differentiate this. Okay, differentiate this to give plus 2 times 3 over 81x cubed. Squared. We differentiated x cubed to give 3x squared. Okay, and then plus dot dot dot. Okay, almost there. So then we multiply the half into the bracket to each term. With each term we get, okay, half times 2/3 is 1/3. Third minus half times this gives 2/9 x, and let's do some cancelling here. Divide by 3, divide that by 3, 27, and the half and the 2 there cancel. So we get 1 over 27x squared plus dot dot dot. And this is the answer to the last part.